Hi, I'm Dominik Steinwürfel, and in this talk, I'm going to tell you how you can model program transformation rules and automatically prove properties about them, like preservation of program semantics or reduction of execution cost, such that you don't have to be afraid applying them to systems that you better should not break. So assume that in your basement, you have a funny device like this here, running Steam programs, like the real Steam, not the gaming platform. And at one point, you probably think that maybe you better would like to program in Python instead of Steam, or use Node.js with some cloud platform. So you maybe replace this computer with something new and also write the program from scratch or somehow do transformations for your existing Steam programs. Nothing about this is particularly problematic, but if we now assume that this computer is not in your basement, but in the basement of some fintech company where it does like stock trading, then it's suddenly a legacy system since it's business critical and the company does not want it to fail since this would have a significant impact on the business. What does impact mean in that case? Well, usually it means that if this system breaks down, you lose money. And losing money is something that industry companies, how should I say it, don't like so much. All right, so this is kind of a problem, right? Because you have that system there, it runs Steam programs, but you don't want it you don't want to touch it since it produces value for your company. But on the other hand, it's problematic to keep it running, right? Like in this headline here, companies become prisoners of their legacy systems. On this one here, legacy becomes lost since keeping that system running is increasingly expensive since you don't have much documentation, your original developers might no longer be present. You are developing in technologies that have been developed before, like the widespread use of modern software engineering technologies and best practices. So this is a problem. And even worse, you might not even know whether or how many legacy systems you have or how much they cost you. And if there are numbers, those numbers can be quite scary, right? Like this one here, where obviously the US economy loses huge amount of money, is partly due to legacy systems. So this is a problem, and getting rid of legacy systems is a huge challenge. What we would like to do is to take this program here that runs in our Steam computer, which produces money, but costs increasing amounts of money, and somehow change this to a program using like modern architecture and techniques, like, cloud services and parallel pipelines. And it's also like sufficiently documented, and it should run on modern computers like these computing centers also. Question now is, how can we do this without losing the precious functionality of our original program? And that's a challenge that our developer that we have here is now facing. Software reengineering now is a general approach to give structure to this kind of process and studying how it might work. Usually it's defined like follows. You first have a reverse engineering case where you have a look at the system and try to gain more knowledge about it, right? Like have a look at the particular components, like the databases, the program chunks, and maybe find some of the documentation here. And then also you produce additional documentation and define your restructuring goals. When you have done this sufficiently intense, you can proceed with the forward engineering phase, where you actually take the system with the improved understanding about it and apply some transformations, which eventually lead to a system like this one here, that is of the shape that we are desiring, right? So now the question is, does the system still produce money? And take into account that the original developers, so these are developers of the past, as you can tell from the hairstyle, might no longer work in the company, and also the documentation, if it ever existed, might be outdated or somehow lost. That means that testing the system can be itself quite challenging, since you don't have like a test oracle, so you don't know what this particular code was supposed to do, right? And this even if you had this first phase of the reengineering, because I mean, there is no guarantee that this is hopefully successful. So this is still a problem, and what should we do now to guarantee that this whole process doesn't burn the money of our company? What I propose now is to replace this second phase of the re-engineering, where you do some arbitrary changes, where you shuffle with code and some programming, with a more structured approach based on a catalog of existing transformation rules and techniques. And now applying these rules from the catalog readily to our input system leads to systems that are more and more closer to our resulting system. And the interesting part is, if we somehow manage to prove that the rules in our catalog preserve the semantics of the input systems that you feed into these transformations, and what is more, if you can even prove additional non-functional properties like no, the output system runs quicker, or it's usually better maintainable or better understandable, then you get all these properties for your intermediate systems and also for the final system, which means that this system now produces still money and maybe even more, since it's better understandable and runs quicker. Okay, to be fair, I just replaced this problem of how to change the system and do post-hoc verification and so on with a problem of coming up with this catalog of transformation techniques, right? Well, one could say that it's unrealistic, right? And you don't have these catalogs, but these catalogs exist, at least for certain domains. For instance, here is a catalog of refactoring techniques. So there's techniques that aim at preserving the semantics of input programs, but making them better readable and better understandable for actual humans, which should improve the maintainability of our system. So this refactoring catalog here has been designed by Martin Fowler, who also has written two quite popular textbooks on the subject. And refactorings are implemented in basically all IDEs that I know. For instance, here you see IntelliJ. And you can, for instance, move your cursor to a line and press this combination here to move the statement once up. But now you see that you broke the program, since you are referring to this variable x before its declaration in the now second line. So this means that using refactoring, if you don't have sufficient checks and know what it's doing, can break programs, right? And this happens. Let's have a look at a more complicated example here. So we have this chunk, this three-liner, this if statement with a return that we now want to extract in our method, and there is a shortcut for this. And here we see that, well, actually IntelliJ made it correctly, right? So, but you see that it's quite complicated. Instead of an int, this method here returns a non-trivial integer type and uses a null value to signal that there was no return inside the extracted fragment. And this then here is distinguished to forward this abrupt control flow, this return to the outer context. And you can imagine that if this gets more complex, like if this already would be like an integer, or if you have like multiple returns or whatever, this can get quite elaborate. And I don't know whether IntelliJ does this all correct. But the message here is that it's a challenge even for these quite well understood and well documented rules to get their correctness right. So it's an interesting endeavor to actually try to prove circumstances under which applying these rules, these transformations is correct. So at that point, I could give you an overview slide of my talk, but I would rather show you this comic. And instead tell you that now I'm going to tell you about a technique that I designed for proving the correctness of transformations in statement level under preconditions. And I will tell you about three interesting applications of this technique in various areas. All right, the technique that I came up with in my PhD thesis is called Abstract Execution, which is the symbolic execution of abstract programs. So an abstract program is just like a program with some placeholders, right? An abstract execution reasons about all instantiations of these placeholders, not taking into account whether these placeholders are instantiated with an if statement or a loop or whatever, but only talking about the behavior of these things, like their big step semantics. So an abstract program can be something like this here. So each of these symbols represents like an arbitrary statement. And if you now have a pair of them that you can also give a name, then you suddenly don't have an abstract program anymore, but a transformation rule. This rule, for instance, tells you that you have a program that you can divide into two statements, and you just like reverse their order. And this is in fact an existing refactoring rule. It's actually the first one that I've shown you in this IntelliJ example slide statements, where you reverse the order of two statements. And now we want to somehow model this such that it only represents circumstances when you can safely apply this kind of transformation. And this works like follows. So first you give names to the locations that are assigned and accessed. That is like written in red by these placeholders. And you can also specify their abrupt completion behavior. For instance, here for simplicity, we say that we for now only consider instantiations that complete normally, that for instance do not throw an exception. We can do the same thing for our second placeholder. And now we have these symbols, right? We know that this thing here writes to some set of locations that I call pink W blocks. And I can define constraints on the transformation level about these placeholders. For instance, what this here says is that neither statement influences the other one by writing the locations that one reads. And also neither statement does overwrite locations written by the other one. And under these circumstances, when these placeholders are independent, you can just safely go and swap them. In reality, I don't use font awesome symbols, but an extension of the Java language in my implementation, which works based on the key program rule platform. So when you declare an abstract statement, you write \abstract statement and then a name. So instead of colors, you have names, such that you can have these pairs of programs with the same elements that are linked by their name. And for defining their behavior, I use these comments in the Java modeling language. So here I say that P writes to an assignable set of locations frame P and reads from an accessible set of locations footprint P, and likewise for Q. So abstract execution is the symbolic execution of such abstract programs. And symbolic execution works like that. So you basically have a symbolic store, which is an abstract representation of memory. And if you now execute this program, you do it in like a forward symbolic execution from the top to the bottom. So you start with the first statement. And what you do here is you, since this thing does always complete normal, you can just like project this assignment to the store. And the store now represents an infinite set of complete stores, right, for any initial value of this variable set. If we have case distinctions like this if statement here, then we follow both paths independently. And these case distinctions update the so-called path condition for the store. So we spawn another store and we condition it with some formula here. So whenever a is greater or equal to 0, this means that in this place here, actually the initial value of set is greater or equal to 0. So this is the current value of A here. And in the case where we would enter it at the else branch, set would be smaller than 0. And now we continue along these branches. So first we hit this abstract statement here. And now again, if we assume just for now that we don't have abrupt completion here, that this just like does some like changes to frame P, reading some of the locations to footprint P, where both of them are upper bounds, right? So instantiations of P might also just not write anything or write everything in frame P. So if we assume that this just completes normally, we can basically do the same thing as for this trivial assignment here. We can just write these changes over there. And since these are abstract changes, we need an abstract way of representing these assignments to the store. And this works via an abstract update. And you see that it looks quite similarly to the abstract statement, right? We have the name, it's UP, and we have like assignable and accessible locations separated by some query assignment operator. And not taking into account the completion, the semantics of the update and the statement, are exactly the same, similarly as for this elementary update here and this assignment here, right? And now we continue. So now we enter the else branch and write an abstract update corresponding to Q, UQ, to the other store, and finally execute our return statement. So now we have stores like this, and we probably want to know what the value of result is, right? And this depends on the behavior of this abstract update. So if the abstract update, for instance, writes to A, this will be a different result than if the abstract update just writes to some other set of locations, not including A, right? And also, it's interesting whether the abstract update reads in its footprint this assigned value A here or not. And so how so we need some simplification rules for these abstract stores that take into account conditions that we specified on our abstract statements. So how this works is, since I implemented this for the key prover, our abstract stores are represented by key updates. So that store would be just like a sequence of such update applications. And first, we can make use of all the existing update simplification rules that are already there in key, right? We can combine the sequential updates to parallel ones by like shifting this inside here and combining this to a parallel update and so on. And now at this point here, we have expressions like this inner one here that we now have to take care of. And here, actually, my update simplification rules for abstract updates step into the play. Well, actually, at that point, without any additional assumptions, we cannot do anything, right? Since we don't know more about P. But if we know, for instance, that this location A, that is the target of this update application, is disjoint from frame P, that is the assignments of the abstract update are irrelevant for the target location, we can just drop the abstract update, coming up with this expression here, which further simplifies to simply the initial value of set. If this is not the case, so A could be in frame P, but we know that this A here is not in this A here is not in footprint P, then we can drop this initial update here, right? Since it is irrelevant for the locations that are read by our abstract update instantiations, and we get a little bit simpler expression. So I mentioned before that these frames and footprints that we have here are actually over approximations. So this talks about all instances of this update that write at most to the locations in frame P and read at most the locations in footprint P. But sometimes we also want to have models where we say something like, okay, this update definitely has to assign some location, since, well, I only want to consider these instantiations, and then we can do more aggressive simplifications. For instance, if we assume that frame P definitely has to assign A, so every instantiation of the abstract update writes to the location A, then we can also drop this initial update in the parallel composition here, getting an expression like this one here, consisting only of the abstract update applied to variable A. All right, so this is all for the case where we don't have abrupt completion, right? So we just project the abstractness of the statement with the abstract store. But of course, we have to take care of abrupt completion, since an abstract statement which represents any complete statement, well, can also complete abruptly for any reason if we don't specify that instantiations should not do this. So what we do here is, as usual in symbolic execution, we perform a case distinction. Either we complete normally, and then our initial symbolic state consisting of path condition in the store is transformed to this as normal state containing the abstract update, or we, from exception, return, break, or continue. And also there are cases in Java where we have labeled breaks and continues. All this has to be considered. And for all these cases, a suitable symbolic state is generated like this one here, which will then assign a suitable symbolic value to our programmable res, and that is returned for the return of a value case. Okay, and then we can just normally continue symbolic execution as I've shown you in the example before. Right, to make this more fun to work with, I created a graphical workbench called REFINITY. You see a screenshot here, which lets you specify pairs of programs to model transformation rules with abstract execution. And REFINITY has some editing support. It also generates proof obligations for the key prover, which otherwise would be a huge amount of work. And I'm quite happy to say that this already has been used in a tutorial session in 2019. And those people there actually managed to model and include some easy refactoring rules themselves in the limited time span that we had at our hands. And so this is a quite successful story. And now it's time for a demo where I will actually show you how REFINITY works for a non-trivial example. So this is the window of the key program prover, and if you check out the right branch, then you have a big REFINITY button here. What I am now going to do is I will model a refactoring rule called replace exception with test. The idea is the follows. So I have like some statement which, for instance, looks like this. So I can keep a quotient of two numbers. So I don't want to declare these variables here, since I want to use them on left and right hand sides both. So I declare them as three broken variables that I don't have to declare. So they are declared somewhere outside the context of the appearance of the statement, right? And since I'm an astute programmer, I know that this will throw an exception, namely an arithmetic exception if y is 0. So what I do is I just wrap this into a try catch block and catch my arithmetic exception. And in the case that this exception is thrown, I assign to Q a dedicated value to signal to the outside that this exception occurred. Of course, Q will never attain the value for it otherwise, right? So now what this refactoring technique, replace exception with test, is saying is that this is actually code smell. So this is not something that you would like to have. Since, right, I mean, you know that an exception happens, and you also know when it happens, right, as a programmer. So this happens when y is 0. So we could just replace this try catch with a check for zeroness of our variable y, and only if y is non-zero we perform our revision, and otherwise we assign the default right. And now the result is that the condition of the exception is much more explicit, right? So here this is a special case, and if this special case occurs, then we do something special. While this is quite, it's a little bit more non-transparent for readers of this program what happens here if they don't know, about the arithmetic exception, for instance. So in REFINITY now we have these two pairs here of programs, and we can prove that they are equal. You see here on the right hand side of in the right bottom of the window, we have this relation post condition saying the result on the left should be the result on the right. And result means like all returned values, all thrown exceptions, and also all locations that I declare relevant, right? So as a standard, we have an abstract location set here called relevant, but for now, for this simple example, I want to simply talk about our variable q. So this is the relevant location that should have the same value after executing both programs. And now if I press play, REFINITY will create a proof obligation for a key and have some status information here. So currently no proof, and now there should actually be running. Yes, running. And as we see, key finished the proof, and it's now closed. And we can now save this proof here, and we can also later on use this proof certificate to validate that this pair of programs is equivalent. And yeah, this is what REFINITY does. So it looks like the idea of this refactoring technique, replace exception with test, is sound. So let us now model this as an abstract transformation rule using abstract program elements, abstract statements, and expressions. So what we again have is a try catch. I will now catch an arbitrary throwable, since we are not only talking about repeat exceptions. And here, instead of the division, I have an abstract statement here representing an arbitrary concrete statement. So I could now write abstract statements and so on, but Refinity has some editing support here. So if I write AS and then press a shortcut, Command Shift Space on Mac, then I get like this stub here. And now we see that I have an abstract statement with some name and which has some locations that it may write and some locations that it may read. Maybe we will rename this to try statement and call this frame try and try. And these specifications here say that instantiations of this try statement may not, from exception, return, break, or continue. I will, for now, remove these ones here. So instantiations may return here. I actually don't care for this transformation. And now, if an exception should be thrown, then we have some catch statements here. Catch statement where it's all frame and footprint. So Refinity interfaces to key to offer us some non-trivial syntax checking, so you don't see any problems here, but because it takes just too long to check. But if you press this button, then we will probably get reported that something is not okay. So let's see, what does it say? Frame try cannot be resolved. Yes. So similarly as for the three variables that we had before, we have to declare these symbols. But in this case, they are not variables, but some placeholders or location sets. So let's just declare them. Frame try, footprint try, frame catch, and now run the syntax check again, and it looks like everything is all right. Okay, and now we would like to transform this thing here to an if else, right? So we need here this will be then the else. Nice, and here we have an if. So, but what to write inside this if expression here? What is the guard of the if? And so what should be the guard? The guard should be the negated condition under which try statement throws an exception. So we need to somehow give a name to this condition, right? And this works by specifying not false as a precondition for try statement, but giving it, but using some abstract expression. So what we do not want to do here is we do not want to restrict the conditions under which an exception is thrown, but we want to give them a name, such we have a handle for referring to that name, to this condition later on. And we can do this by using an abstract predicate. Let's call it throws try. So the condition under which try throws an exception. This is just like an abstract predicate that I will declare in a minute. And this depends on a set of values, right? Because here this statement only throws an exception if y is 0 and not otherwise. So this condition has to be context sensitive, so to say. So footprint try. And there is something to consider, and this is that footprint try is, so to say, a static descriptor of a set of locations, which does not change over time. But what we are interested in here is the particular value, the evaluation of the set at this point in the program execution. And to access this, we wrap the footprint try with a value function here, right? Backslash value. So, and now we know that this throws an exception if throws try holds. We need also to declare this predicate. So throws try, which depends on something. We don't know the type of the instantiation footprint try, so we have any. And now we can also use this here. And what we need here is an expression at this point, so not a statement. Luckily, the execution also comes with a abstract expression statement type, expression type there, so which has a name. Boolean is just correct here. This should not have side effects, actually not have any side effects, so nothing should be assigned here. And it should access the locations that also try statement has access to, and should evaluate to true if and only if this expression here evaluates to false. So what we do here is we restrict the result value of the expression, this one here. And what we have to do is, unfortunately, we have to cast this to a Boolean, since well, since this is of object type in general here, and otherwise we get an exception. All right, so this looks like it's what we want to have, and we can now first maybe apply a syntax check here. Oh, we have a problem. Let's see what this is. Exception. Oh, actually, we need to have normal behavior here, since otherwise we don't have a result. And this exceptional behavior should not occur, right? So we specify exceptional behavior requires false, since we don't want our check here to actually throw an exception. So still, there is a problem here. So this is a live demo. So we actually don't want to require the result to equal in this expression, but we want to ensure it. So since we want to talk about the post condition and not the trigger for the normal behavior. And still we have a problem. What's the problem here? Ensures, not ensure. So this is a nice demonstration of the syntax checking capabilities of REFINITY. And now it's actually okay. So we can press the play button and feed our proof to key. So we see that now it's registering rules, and the proof obligation will be generated. Here it is. I'm really happy that I don't have to write smooth step every time. So this is what REFINITY does for you. Proof starts. So let's see what happens. It takes some time, but take into account that if we manage to prove this here, then this is a quite strong result for all programs. Imagine our left program, we get the result on the right. So this is not just this is a once and for all result here. This is what I want to say. So we see that unfortunately 4 goals remain open, and these things look quite complicated. And actually, I also used a non-trivial example for this demo. So what we want to have is we want these predicates P, which represent the result of the left program, and the predicate Q, which represent the result of the right program, to have the same content. Here on well, maybe we can use Unicode symbols. Yes. In the first slot of these predicates, we have a returned value. In the second slot, we have a thrown exception. In the third, we have the values of all our relevant locations, which is this relevant location set here, and this should be the same. We see that this is not the case, since here we have our catch statement has executed also, but here the try statement has executed before, and that means that the value of the locations that the catch statement is accessing here may have been changed by the try statement. And this is actually a problem. So the situation in the concrete example that we have here is maybe that one. So assume that we have an assignment here, and we are also interested in the final value of our program variable x. Okay. So if we now try to prove this, this will fail. And why? Because if y is 0, then here we will first execute this incrementation and then throw the exception. So otherwise, so as a result, x will have like the value increased by 1 compared to its initial value. While here we first check the condition and directly step into the else branch, so x will retain its original value. That means that generally you cannot apply this transformation as is, but only under certain preconditions. So here we see the result. It's a bit simpler to digest than the one for the abstract case. So here we have 1 plus x for x and the original value of x for the other side. Okay, so we have to do something, right? And what can we do? So what we can do is, for instance, we can say, okay, this transformation is sound whenever you have a program which first resets the interesting locations to some standard value, right? Like here, because then whatever happens when executing the catch statement, we have the same values for our execute. And now if we prove this concrete equivalence, it should work. So I call this a rollback statement. And we can also model this in the abstract case. There are also other possibilities. For instance, if like the frame of this works, if the frame of this catch statement is the same as the frame of the try statement with a has to, then this also works. But actually, this is kind of a recipe. So if you want to apply this transformation, maybe add a reset before a rollback, and then it's safe to do. So what I will now do is I will declare this this rollback statement that will that has to override all the frame of try while having access to its own footprint. And the interesting thing here is that this footprint must be independent of the frame of try, right? Because otherwise we're in the same situation. If I assign to x like the value of x, then we don't have any improvement. So I will now declare a constraint saying that the frame of try and the footprint of rollback are disjoint, and I can do this by writing abstract AE, like abstract execution constraint disjoint, and the arguments of this are frame try and footprint rollback, and I also have to copy this for our target program here. So that's the same thing, and also add the rollback statement, of course, because otherwise I have totally different programs. All right, I guess that should be fine. So let's see whether there are any typos and everything's correct. Oops. Oh yeah, I did not do my syntax check before, which was bad. So I first have to declare also the rollback, and let's now do the syntax check. Right. Okay. So now we are hopefully able to prove this thing, which means that now we have a model for like one application scenario of replace exception with test, which does not change the semantics of the input program. So the proof did not start automatically, unfortunately, so I still can press the play button to mitigate this. Not much work. This is some kind of threading problem I was not be able to resolve well. So, and this time the proof works, so it's actually correct. Okay. So this was the demo. Here's my face again. Right. Generally, how it works when you want to get like these preconditions that are sufficient for safe application of transformations. You start somewhere with some transformation model, generate goals with REFINITY, have a key proof, and then if the proof is closed, you can just save the certificate and are fine. Otherwise, as I did before, you have a look into the failed proof and try to derive, from this failed proof attempt feedback on how to refine the model, and then you loop here until at the end you get your proof certificate, and this is how I derived all the preconditions for safe applications for my case studies. So speaking of case studies, this is not a work of pure theory. We have a number of interesting applications here, and I will talk about 3 of those in the remainder of this presentation. First, I have already mentioned refactoring techniques, which was like the flagship application in my PhD thesis. Another interesting application is the cost effect of transformation. So if I apply a transformation and maybe assume that it doesn't change semantics, what effect does it have on like the runtime or the space consumption of the input program? And next, we had a collaboration where we focused on the parallelization of sequential legacy code, right? So for refactorings, I will just present you the results since we already had the demo. So I had a look at 9 of these statement level refactoring techniques. All of these proofs that I had once I had the model corrector fully automatic, and also proofs for problems with loops, since I found a generic specification mechanism that works for these abstract models. So I didn't even have to come up with difficult loop invariants, so it can basically generically plug them in. And for all of these refactoring techniques, although refactoring is something really well known, well studied, there are books about it in publications, I found new non-trivial preconditions. In one interesting example, actually, the precondition was that there is no precondition, although the book said that there is one. So also this happens when we talk about program transformations. So then just imagine that you have a program and you pull out a prefix here, maybe because like this is a loop invariant prefix. And then the intuition would be that this is now free to execute, right? And, well, it's generally true. At least it doesn't get more expensive, but it would be nice to prove this and also to have a look at the cost effect of more involved transformations than this code motion example here. And well, what we did is here with a collaboration of with a team of the University of Madrid that have a nice cost analyzer for hand, we derive abstract cost expressions from these programs. So what you see here is the cost of the ping program, whatever it is, depending on the cost footprint of the program. And here we have a corresponding expression for our orange program. And then we get another expression like this for the red program. And comparing these expressions, we then actually can deduce that executing this program is cheaper. And what we did here is we did not only just extract some expressions, say, okay, we are fine, but we modeled we wrote the cost model into our abstract program model to actually prove that these are the correct cost expressions, right? And if and this happens in quite a number of cases, the cost analyzer is too optimistic and gives us a wrong result, then we can automatically switch to a weaker cost model, for instance, going from precise cost to upper bound to asymptotic cost, and all this with a fully automatic collaboration between the analyzer and the prover. In this case study, we had a look at 7 loop optimizations, so all examples were with loops, and even though we have fully automatic analysis and proofs, and this is not, well, this is not clear that this works, but the cost analyzer was able to give us really good feedback on the required annotations for our abstract program models, including the cost invariance. And this was actually not only the first approach to automatically address the cost impact of transformation rules, but the first approach to do so at all. So this is quite an interesting result here. Right, and the last application that I want to talk about today is about the parallelization of code. So assume that you have this code here and you want to somehow run like these 2 things in parallel, assuming that they are independent. Then our collaboration partners from the University of Darmstadt have a tool which which comes with a number of parallelization patterns, right? So whenever a program has a certain shape, you can parallelize this using some OP pragmas. So this program here, unfortunately, is not in the shape that matches these any of these patterns of the catalog. So what these people are doing is they also have a number of transformations of sequential programs. So for instance, here we can split this loop, and now, this matches the pattern that we want, and we can apply a parallel pipeline, for instance. So we have a sequence like this, starting from an initial sequential program. We do some sequential optimizations or transformations, and then we have the parallelization optimization. So our contribution here was to model and prove this part here from sequential to sequential. And actually, this is, well, we don't only have the correctness result, it's the first mechanic, like the precise documentation of these transformation that these people apply. So it's actually also there a nice contribution. And then we can do the parallelization. And this gives us now more safety in this parallelization, which before was maybe a little overly optimistic. We had a look at 3 of these regularly used transformations, which are quite complex. For instance, they deal with like nested loops, like dividing memory structures in different regions. One of these is called, for instance, geometric decomposition. And for this example, I had to come up with a new specification mechanism for, as you see here, an abstract memory regions, which is like a new specification mechanism for which we don't have yet sufficient proof support for change. We don't have fully automatic proofs, but merely more than 99.7% automation, and we get, as I said, more safety for this parallelization. All right, there's a number of future work here that we can address. So just like having a look at this idea of structured software reengineering, we of course want to extend our catalog of transformations. And like doing so will also improve the techniques that we have. For instance, it would be nice to get like more direct feedback from failed proof attempts here, right? Or have a look at different kinds of areas. We already had a look at cost analysis. There might be more things that are really interesting, and there might be transformations about statement level and what have you. Once we assume that we have such a catalog, we could actually like implement, for instance, IDE support, such that we can have like we choose split loop, and then we say that okay, the cost effect is minor, but maybe then we separate the concerns, and then we drag and drop it to our code, and it will only be applied if preconditions match, or we get automated tests, or what have you. This would be quite nice. All right, so I talked about in this presentation about my vision of structured software reengineering based on the catalog of broken transformations, and a particular technical contribution for automatically proving the correctness of statement level transformation rules, which I implemented for the Java language called Asterisk Execution. I've shown you how to use it with my tool REFINITY. I also have like this demo proving the replace exception with test refactoring, and I've presented a number of interesting case studies. There are more case studies now which are also currently going on, but these are some of the most interesting ones that are already concluded. So if you are interested in my work on this topic, then here is some contact data. So just write me, drop me a message, and I hope to enjoy this talk and that particular work, and maybe you want to try out REFINITY yourself in the future. Thank you very much.